Hey everybody. Today we're talking about hypothesis tests for proportions. We're in a situation where there's an unknown population proportion, p, and we want to know whether one particular value, p naught, is plausible or not in light of some sample data. In other words, we want to test the null hypothesis that p is equal to p naught. The process for such a hypothesis test is really identical to the process for a hypothesis test for the mean. You start by stating null and alternative hypotheses carefully. You need to choose wisely between a one-sided and two-sided alternative. You compute a test statistic using your sample data, and then use that test statistic to compute a p-value for the test. You then use that p-value to make a decision about whether to reject the null hypothesis or not. Ultimately, you want to state your conclusion in ordinary human language, saying something that a non-statistician can understand. According to the central limit theorem, the sampling distribution of the sample proportion p hat is approximately normal with mean p naught, where p naught is the value we're assuming from the null hypothesis, and standard deviation square root of p naught times 1 minus p naught over n. I talk about these formulas in some depth in my vid on confidence intervals for proportions. If you haven't seen that or you just need a refresher, I'll have a link up top. Now, since p hat has a normal distribution, it makes sense to compute a z-score as our test statistic. So we take the value we observed, p hat, we subtract off the value we expected, p naught, and then divide by the standard deviation of that sample proportion. So that's that square root in the denominator here. And this test statistic has a standard normal distribution when the null hypothesis is true, and we can use it to compute our p-value. Let's do that in the context of an example. A commenter claims that 30% of 6-year-olds in the United States have a zinc deficiency. In a random sample of 64 6-year-olds, we find 8 with zinc deficiencies. Is there sufficient evidence to reject the commenter's claim? Test at significance level alpha equals 0.05. In this case, we're going to choose a two-sided alternative. There's no reason to assume that p can't be larger than 30% or that it can't be smaller than 30%. We're interested in both those possibilities. So our null hypothesis is that p is 0.30. The alternative is that it's not 0.30. Here, p naught is 0.30. When in doubt, by the way, you should always choose a two-sided alternative. That's the more conservative option in the sense that it has the lower risk of a type 1 error, a false positive. Since 8 of our 54 subjects have zinc deficiencies, our sample proportion p hat is 8/54 or 0.148. We have a p naught value of 0.30 and an n of 54. We plug all those things in, do a little bit of arithmetic, and get negative 2.44. We recognize that that is an unusually negative z-score. 95% of z-scores, when we're just doing random selection, fall between -2 and +2. But it's not a radically negative z-score. We can be more specific about how radical it is by computing a p-value. That is, we want to compute the probability of randomly getting a z-score more extreme than what we actually computed just by random chance in that standard normal distribution. And that corresponds to the probability of randomly getting a p hat more extreme than the one we observed when the null hypothesis is true. In other words, we need to compute the shaded area that I have here. We're going to compute this using the CDF of the standard normal distribution, the cumulative distribution function. And that gives the area to the left, the probability to the left, of any specified z-score. Tables exist for that, but that's very old school. I recommend using technology. I use R, where the command for the CDF of the standard normal is pnorm. So pnorm of -2.44 is giving the shaded area just on the left there, which it turns out to be 0.007. The p-value of the test is twice that, because we have symmetry in this distribution, so the total area is twice the area on the left. P equals 0.014. This is smaller than the significance level that we set at the beginning of the problem, alpha equals 0.05. So we reject the null hypothesis and conclude that the proportion of 6-year-olds in this population that have zinc deficiencies is not actually 30%.